Good afternoon, everyone. My name is Ming. I will be talking about our work of applying AOD in keyword search. This is joint work with Chunxi, Sanjeev, Lukash, Shenji, Luca, and Ajim. So far, we have presented the results of using normalized mutual information to evaluate the performance of AOD. Besides, we are also interested in going beyond the transcribed phones and be able to do some extrinsic measure of AOD performance. For example, the same different task. The idea is, given a pair of acoustic segments, we want to tell if those segments contain the same word or not. This is relevant to the query by example keyword sporting. For example, the left side pair has two segments for the word record. We want to be able to tell those segments contain the same word because their representations are similar to each other. On the right side, there's one segment for the word record and the other segment for the word maintenance. We want to be able to tell those are two different words because their representations are quite different. This semi-different task can be used to quantify the ability of a speech representation to associate words of the same type and to discriminate different word types. In order to measure the performance of same-different task, first we do compute the pairwise similarity of two speech segments using the dynamic time warping DTW. The idea of DTW is shown in this picture. It's widely used to find the best matching of two sequences, A and B here, and these two sequences could have different lengths. Here we use the cosine distance to compute the DTW similarity. Once we have the similarity score for every pair of segments, we are able to make the same difference decision by setting a threshold. And further, we are able to plot the precision recall curve for all the pairs by changing the threshold. Here is one example of the precision recall curve. And finally, we are able to compute the average performance across different operating points. That is, we compute the average precision as the area under the curve. Here we use the average precision as the reported metric for the same different task. The high number of average precision means better performance of same different task. For our experiment, we use the TMIT dataset. There are in total 4,600 utterances that counts for more than 3 hours. We select roughly 2,200 different word types. All the words selected are at least half second long and contains at least 6 letters. There are in total 5,200 word tokens. We try 2 different types of features. The baseline feature is the MFCC with first and second order derivatives. There are in total 39 dimensions for the baseline MFCC features. The other type of features are the posteriors from the AOD. For example, here we have 3 acoustic units. Each one has a 3 stage HMM to model it. Given an input frame of MFCC features, we are able to compute the state level posteriors, which are the green numbers here, as well as the unit level posteriors, which are the red numbers. Here, the unit level posterior is computed as the sum of all the corresponding state level posteriors. The idea is by clustering the frames into different acoustic units, we are able to get better representations to discriminate different words. We also noticed that the posteriors for the AOD are quite peaky. That is, mostly there is one dimension with a very high number, and all the other dimensions are close to 0. As a result, we use the acoustic scale to smooth the posterior and get a smoother distribution, which tends to be very important for this same-different task. Our results of comparing different AOD settings against the MFCC baseline are shown in this table. And here we can see that for the MFCC baseline, it gives the average precision of 0.484. We try different number of units, as well as the single HMM state AOD, which is the first column, and the 3-stage AOD, which is the second and third column. From the previous slides, we see that when we use 3-stage HMM AOD, we are able to have either the unit level posteriors, which is the second column, and the state level posteriors, which is the last column. From the table, we can see that all the AUD posteriors perform better than the MFCC baseline. If you look at the first line, which is the 50 units, the three-state AUD unit posteriors is better than the single-state AUD posteriors because it uses the HMM to model the temporal information. And further, if we use the HMM states posteriors, that has higher resolution and gives even better performance, which is 0.618. When we increase the number of units to 100, the three-state AUD posteriors perform similar, and the single-state AUD posteriors improves. When we increase the number of units further to 200, the single-state AUD posterior starts to drop, while the three-state AUD posterior keeps improving. We stop our experiment at 200 units for the configuration exploring. So far, the best performance comes from the 200 units and 3 HMM state level posteriors, which gives the 0.639 average precision compared to the MFCC baseline, that is 32% relative improvement. Based on our experimental results, the automatic units outperforms MFCC in the same different task, and this could help improve the keyword search. Yeah.
Ask for a quick clarification. So the first column, that you have AUDs with S equals 1.
Yeah.
So this is like the GMM that Vivo was presenting? Are these AUDs like that?
This is like single state, single GMM. That could be equivalent to DPGMM.
One is like Luca or Elena or all these people. It's a three-state, but you're adding up the specific probability three-state as an HMM.
Yes, as the red number here. Okay. Yeah. And next, Santos will talking about another measure of the AUD performance.